Hello everyone, good evening all. Welcome to Unacademy. This is Bhanu Prakash, expert in GATE and ESE. I did MTech from NIT Kurukshetra. I have 10 years of teaching experience and I train many students throughout our country for different competitive exams like GATE, ESE, Transco and Genco. My subjects are electrical machines and power electronics. PPC 10 is my referral code. So use this code, you will get 10% discount on Plus subscription as well as Iconic subscription. Okay. And what are the benefits of the Plus and Iconic subscription? So by taking Plus subscription, you will get live classes from the top educators of the country and also test series, structural schedule, unlimited practice question and ESC mains questions and answers. Okay, BPC 10 is my referral code. Okay, use this code, you will get 10% discount on Plus subscription and Iconic subscription. Okay, and this is the another subscription. It is the Iconic subscription. By taking Iconic subscription, you can get 4 benefits. In addition to these, you will get some extra benefit. One is a personal coach, study planner, expert guidance, CSC mains questions and answer. That means we will assign a personal coach. He will guide everything until you reach your goal. And study planners, you will provide the proper study planner, how to prepare GATE and how to prepare ESE. And expert guidance, we will provide the expert guidance and also we will provide ESE mains questions and answers. So this preparation, this subscription, it is a very suitable for the ESE preparation. Okay, so take this subscription, use this opportunity and use my code BPC10. You will get 10% discount on Plus subscription as well as Iconic subscription. And what are the price for the Plus and Iconic subscription? So it is available for, okay, this is the available the further this that 12 months, 18 months and 24 months. For 12 months fee is the for 27,225 rupees. For 18 months the fee is at 34,650 rupees. For 24 months fee is the 39,600 rupees. Okay, and next one one more subscription, that is the Iconic subscription. So it is available for 12 months and 24 months. For 12 months fee is 45,225 rupees. For 24 months fee is 66,600 rupees. BPC 10 is my referral code. Use this code, you will get 10% discount on Plus and Iconic subscriptions. Okay. Let us solve this question initially. So this was question number 1. Okay, this question belongs to 3-phase transformer connections. A 3-phase delta star transformer has a secondary to primary turns ratio per phase of 5, and per primary voltage of the 400 volts, the secondary voltage would be options given 2000 volts, option B is 80 volts, option C is the 3464 volts, and option D is a 104 volts. Okay. So A transformer ichar ikkada delta star transformers. Given transformer is a delta star. Okay, turns ratio mentioned, that is the turns ratio, the as secondary to primary turns ratio is given. So first let us find out what is the secondary terminal voltage. Okay, load secondary terminal voltage. How do we get load secondary terminal voltage equation for this transformer connection? Okay, given transformer is a delta star 3-phase transformer. So in delta star 3-phase transformer, first one, let assume supply voltage is equal to V amount of the volts. Okay, this is the known parameters. Let us assume. So supply voltage is a V, and the V1 is a primary line voltage. Okay, V1 is equal to V here, and primary phase voltage V1P. Okay, that is which connection it is? Delta. So in delta connection, line voltage is equal to phase voltage. So that it is equal to V1L. So that equal to V amount of the volts. Okay. And second one, how do we get V2P here? The V2P is equal to the V1P divided by A, where A is a phase turns ratio. So V2P is equal to V by A. Okay. Now we require V2L. How do we get V2L? It is a star connection. So this delta star, in the sense secondary primary windings are connected in the delta connection, whereas secondary windings are connected in the star connections. Okay, this is the connection of secondary windings. Okay, so for star connection, line voltage is equal to √3 times of the phase voltage V2 phase. Okay, అర్థమైందా? V1L is equal to V, V1P is equal to V, V2P is equal to V by A, and V2L is equal to √3 times of the V2P. Okay, and this is equal to, so how do we get the √3 into V2P is equal to, okay, here V2P is the V by, okay, this is the V by A values here. So therefore secondary line voltage we got V2L is equal to the √3 times of the V by A. So given here V is equal to supply voltage is equal to 400 volts, where A is a phase turns ratio. This is the phase turns ratio. So that is a N1. Okay, here N1 phase. Okay, this is a phase turns ratio. Actually, where A is equal to here N1 phase divided by N2 phase. But it was given in this question for primary voltage secondary, that is a secondary to primary turns ratio per phase. So that A is equal to, so this A value is equal to 1 by 5. So now find out V2L is equal to the √3 times multiplied by 1 by 5, sorry, √3 times, where V equal to 400 volts divided by A equal to 1 by 5. So V2L is equal to, V2 is a √3 into 400 multiplied by 5. Now calculate, you will get a answer. Now find out V2L. So this is equal to under √3 times multiplied by 400, okay, into 5 equal to 3464. Okay, this is equal to 3464 volts. Okay, answer for this question is option C is a correct. Okay, like this we have to calculate this question. Now let's move on second question. Okay, this is the question number 2. How do we solve? Let us read the question initially. A 3-phase star delta transformer has secondary to primary turns ratio per phase of 5. For primary voltage of 400 volts, the secondary voltage would be. Option A is given 3464 volts. Option B is 1154. Option C is 2000 volts. Option D is 46.2 volts. Okay, don't need to by heart this formula. By using this connection, you can answer. Okay, here given connection, ఇచ్చిన 3-phase transformer connection అనేది స్టార్ డెల్టా. ఓకే, స్టార్ డెల్టా ట్రాన్స్ఫార్మర్స్ లో సెకండరీ వోల్టేజ్ ఎలా ఫైండ్ అవుట్ చేస్తాం? If we know the primary voltage, you can find out the secondary voltage easily. But here, how do we get that formula to find out the secondary voltage? So see here, the given connection is the star delta 3-phase transformer. So star delta 3-phase transformer means primary windings are connected in the star. Okay, whereas secondary windings are connected in the delta. So let assume the supply voltage is equal to V amount of the volts. So if we know the supply voltage, how do we find out the primary voltage? V1L is equal to V amount of the volts, and V2L is V1P is equal to, so this given connection is a star. So in case of the star connection, so how do we get primary voltage? V1L by root 3. So it is equal to V by the root 3 values. Okay, and the next one, how do we get V2P? So V2P is equal to, okay, this is the V1P divided by phase turns ratio. Okay, phase turns ratio of the 3-phase transformer. After that, so let us find out, okay, V2L. Okay, so this is the V1 by root 3. Okay, this is equal to V by the root 3A. Okay, root 3A. So now V2L is equal to, so V2P because of the delta connection. So that's why we can write V by root 3A, where A is the phase turns ratio of 3-phase transformers. So now let us find out. So therefore the V2L is equal to the V by the root 3A. Okay, V by root 3A. So now calculate, where given in this question the V is equal to supply voltage V equal to 400 volts. And what is the phase turns ratio? Okay, it was given N2 by N1. Okay, this is secondary to the primary per phase turns ratio, where A is equal to 1 by 5. So now simplify this, you will get an answer. So first substitute V2L is equal to V is a 400 divided by root 3 into A equal to 1 by 5. So multiplication 400 into 5 divided by root 3 values. So that here V2L is equal to, calculate V2L. I am also calculating. Let's compare the answers. (400 into 5 divided by root 3). Okay, that equal to 1154.7 volts. Okay, this is the answer for this question. Option B is the correct. Okay, all of you got it? Yes, Maheshwar, good evening. Yeah, you got a correct answer. Option B is a correct. Very good. Vamshi, good evening. Now let us solve another question. So this was question number 3. First read the question, all of you. Then we will solve. A 3-phase star delta transformer has primary to secondary turns ratio per phase of 5. Okay, primary to turns ratio per phase of 5 per primary line current of the 10 amps. Okay, primary line current of 10 amps. secondary line current would be. Secondary line current would. So first derive the formula from the given connection. మనకి ఇచ్చిన కనెక్షన్ ఏంటి? స్టార్ డెల్టా కదా. స్టార్ డెల్టాలో సెకండరీ కరెంట్ ఎలా డిరైవ్ చేస్తాం? ఓకే, డోంట్ బై హార్ట్ ఎనీ ఫార్ములా డైరెక్ట్లీ. సో యూఆర్ గివెన్ దట్ స్టార్ డెల్టా 3-phase transformer. Okay, so star in the means first star. Okay, star, this is nothing but windings are connected in the star. What are they? So one is the primary windings are connected in the star. Okay, and similarly secondary windings are connected in the delta connection. So primary windings అనేవి star లో కనెక్ట్ అయినాయి, సెకండరీ వైండింగ్స్ డెల్టాలో కనెక్ట్ అయినాయి. సో ప్రైమరీ సప్లై కరెంట్ క్వశ్చన్ లో సప్లై కరెంట్ ఇచ్చాడు కాబట్టి సో మనం టర్న్స్ రేషియో యూజ్ చేసి సెకండరీ కరెంట్ ఫైండ్ అవుట్ చేయాలి. దిస్ ఇస్ ద మీనింగ్ ఆఫ్ దిస్ క్వశ్చన్. ఓకే, సో నౌ లెట్ us find first one. Let supply current is equal to, okay, so this is a supply current. So it is the I amps. I is a some value supply current, we know this one. So now let us find out the I1 current, I1L primary line current. How do we get I1L? I1L is equal to I amount of the current. Got it? So this I1L is equal to I, and I1 phase is equal to, okay, so this is a given connection is the star. Okay, star lo phase current line currents same ఉంటాయి. So now here I1P is equal to I1L. So that equal to I amount of the current. Next one, we require the secondary phase current. How do we get secondary phase current? Out I2 phase is equal to A times of the I1 phase. Okay, this is the relation. A times of the I1 phase. So it is equal to, how do we get this A times of I1 phase? So where here is A times of the I. So next one, the delta. So delta లో secondary current ఎలా ఉంటుంది? Line current I2L is equal to, so now this is the delta connection. Currents are not same, so that it is equal to the √3 times of the AI directly you can write, or I2P. So now this is equal to √3 times of AI. Okay, this is a secondary line current. Okay, so now calculate I2L. Therefore I2L is equal to, okay, √3 times of A multiplied by I. So here given I is given, I is equal to how much? 10 amps of the current. Got it? So now where A is equal to, is it 1/5 or 5? Nageshwar, A is equal to, can you tell me A? Is it 1/5 or 5? Okay, A is equal to 5. Why? Because it is given that primary to secondary turns ratio directly mentioned. So therefore A is equal to 5. So now calculate I2L is equal to the √3 into A is the 5 and I equal to 10 amps of the current. So now simplify 50 into √3. 50 into √3, that is a 86.6. √3 into 50 equal to 86.6 amps. So that option B is a correct. Yes, 86.6. Okay, that's correct. Now solve this question. So this is the question number 4. Okay, today we will discuss all the questions, one question series based on the 3-phase transformer. How do we answer this question? A balanced positive sequence 3-phase AC voltage source is connected to the balanced star connected load through the star delta, okay, through the star delta transformers. So this is the star delta transformer as shown in the figure. Okay, the line to line voltage rating is a 230 volts on the star side, okay, and 115 volts on the delta side. Okay, 115 volts on the delta side. Just wait. Delta side. If the magnetizing current is neglected, Is is equal to secondary current is given. Then what is the value of the Ip? Okay, this is the Is. Okay, E current Is antam. Okay, E current nu primary current Ip ani antam. So manak Is ichadu. Okay, Is ent ichadu. So this Is is equal to 100 at an angle of the 0 degree amps. Okay, 0. So next one we have given that. So which transformer here? Star delta transformers. Okay, this is the star delta 3-phase transformer. Okay, primary side are connected in the star. See here, for example, it is a A1. Just assume here A1 and it is a A2. Okay, next one. So this is a B1 and here is a B2. So this is the C1 and the C2. So A2, B2, C2 are connected to the neutral point, one common point. So A1, B1, C1 are connected to this supply source. Now here is a A1, A2 is connected to the B1, B2 is the B2 is connected to the C1. Again C2 is connected to the A1. So this connection is a delta. So now primaries are connected in the star. Okay, whereas secondary windings are connected in the delta. Okay, so then what is the value of primary current Ip? How do we answer this question? So here secondary windings are, let us comes from the secondary. Okay, so now here Is given I2L is equal to, so that is a Is vector, that is equal to 100 at an angle of the 0 degrees. Okay, so now in case of the delta, okay, in delta connection, so what will happen? So that is a I2P is equal to, okay, I2L. So that equal to 100 at an angle of the 0 degrees. Okay. So now we know the relation between these two current this I2PN. So we know that. So that is a I2P is equal to, okay, I2P equal to A times of the I1P. Okay, I1P value here. So now this is a I1P, we required I1P value here. So how do we get I1P here? So that is a I2P divided by A. Okay, I2P divided by A values. So but we here I2P we got 100 at an angle of the 0 degrees, but we don't know where A is nothing but here. So it is a phase turns ratio. Okay, phase turns ratio. So that by using this relation you can get phase turns ratio. How do we get phase turns ratio? A is equal to N1 phase divided by N2 phase. So this also equal to the E1 phase divided by the E2 phase value here. So now this is the, in case of the star connection, okay, it is a connection is star to delta, right? Okay, star side, okay, this line to line voltage is the 230 volts on the star side. So it is a 230 volts on the star side divided by delta side, it is a 115 volts. So now this value is equal to, okay, here V2 pace is equal, V1 pace is equal to 230 divided by root 3, okay, divided by 110. So now simplify this, okay, it is equal to 2 by root 3. Is it correct? 2 by root 3 value, okay, 1. So it is a 2 by root 3 A1. So next find out here I1P is equal to I2P divided by the I2P divided by A. So now this is equal to, that is a 100 at an angle of the 0 degrees divided by A is equal to 2 by 3. So this is equal to the root 3 times of the 50 at an angle of the 0 degrees. Okay. So this is the only, okay, I1P, but we require I1L. Okay, that is a IP. Okay, here primary current. I1L is a required. So it is nothing but, so it is a line current. Okay, line current here. So there is a given that positive phase frequency. Okay, it is a, okay, sorry, just wait. Actually, we did a mistake here. There is a question. So I2P is equal to I1P, but there is a some phase relation we are neglected. That's why we are getting wrong. Okay, that is a is a correct. So this is the positive phase frequency. It is a delta connection. Okay, so this is a, just wait. Here I, this is the I2L is equal to IS. So that is equal to 100 at an angle of the 0, right? So I2P is equal to, okay, per positive phase frequency, positive phase frequency. So I2P is a required. Okay, I2P is a required here. So we know that suppose it is a phase, okay, IA and IB, and this one is the IC, right? IC. So now what about the line current? So per positive phase frequency, it is a minus IB, okay, minus IB1. So now vector sum of these two, you will get the line current, okay, line. So it is a IAB is equal to the vector sum of the IA minus IB vectors, okay, IB. So now what about this is a 120 degrees, okay, it is a 60 degrees, okay, next one the total is a 60 degrees and this is a equal to 30 degrees here. So therefore you can write IAB, the leads IA, by the 30 degrees, the 30 degrees per, okay, all of you got it my point? Leads 30 degrees. So this is in case of the IAB leads IA by 30 degrees per star connections or per delta connections. Okay, delta connection. So next one, see. Suppose in case of the delta connection, like this we have a question. Okay, it is a A1, A2 and this is the B1 and B2 terminals. Very important. Okay, it is a A1, A2 and this is the B1 and B2 terminal and this is the C1 and the C2 terminal. So we required line current. Okay, this is the line current IL. Okay, line current IL, IA. Okay, it is a IB and this one is the IC values here. Okay, so therefore here incoming current and outgoing current. So now this is equal to IA. Okay, it is the IA and IB. Okay, this is the C1 and C2 and it is the IC and this is the IL values here. So now current flows in the A phase. Okay, it is a I A1 A2. Okay, that is the phase current only. Okay, I phase. So in the delta and current flows in the B phase. Okay, this is a I B1 and the B2 terminal. So next one I C1 and the C1 and the C1 and C2. Okay, this is per. Okay, the previously we have discussed about this is the voltages, not the currents. VA, VB, VC here in case of the star. So VAB leads the VAN by 30 degrees in the star connection. So now in case of the delta connection about the currents, okay, here I C1 and C2. So now this is the minus C1 and the C2. So vector sum of these two, you will get the line current IA. Okay, here line current IA here. So now it is lags the by 30 degrees. So therefore you can write, so line current here in delta connection, so line current is equal to root 3 times of the phase current. Okay, phase current at an angle of the minus 30 degrees. Okay, man. So we required I2. Okay, I phase is equal to, okay, I phase. So now simplify here 1 by root 3 times of, okay, 1 by root 3 times of IL at an angle of the minus 30 plus 30 degrees. So this is the formula is required to answer this question. Okay, I thought that initially it is a star, that's why I have given like this, but it's not correct. Okay, so this is the exact vector diagram in the delta connection. So clear point. So IP is equal to 1 by root 3 times of IL plus 30 degrees. Okay, so now simplify here. How do we get IP value? So therefore you can write I2P is equal to that is a I2P is equal to 1 by root 3 times of I2L at an angle of the plus 30 degrees, right? Okay, I2 phase leads by 30 degrees. That's correct. So like this we have to get. So now here 1 by root 3 the into I2 is equal to 100 I2L 100 at an angle of the 0 degrees. Okay, at an angle of the plus 30 degrees. So now simplify this. Okay, here 100 divided by the root 3 at an angle of the plus 30 degrees. So but we required I1 phase. How do we get I1 phase? So we have a formula here. I1 phase is equal to, so that is a, okay, I1 phase is equal to the I2 phase divided by A. So now I2 phase is equal to 100 divided by root 3 at an angle of the plus 30 degrees divided by 2 by root 3. So root 3 will be the cancelled out, so that it is the 50 at an angle of plus 30 degrees. Got it? But we required the line current. In case of the star, the in star connection, okay, star connection. So now it is equal to I1P, I1L is equal to I1P. So now it is equal to the 50 at an angle of plus 30 degrees. Okay, like this we have to calculate. Yes, this is the answer for this question. So initially I was confused here, that's why I have written like, so this no need of. So given I2L is equal to I2L, that is a IS is equal to 100 at an angle of the 0. So answer for this question is 50 at an angle of plus 30 degrees. Option A is the correct. Yes. That's why we got 1 by root 3 into 1 by L, and here is a 50 at an angle of plus 30 degrees. Now let's move on second question. Another possibility question based on this concept. Okay, got it? All of you. This was question gate 2016. A three single phase transformers are connected to form a delta star three phase transformer, 110 volts, 11 kilovolts. The transformer supplies 11 kilovolts load of 8 megawatts at 0.8 power factor lagging to a near power plant. Neglect the transformer losses. The ratio of phase currents divided by phase currents in the delta side to the star connected in the star side. So now here we required, so given transformer is a, okay, delta star three phase transformer. Okay, we required, so I1 phase ratio here, so that is in case of the delta divided by I2 phase, I2 phase in case of the star. So now it is equal to, what is the answer? 1 by A. If we know this A value, so you will get the this ratio. Okay. So now how do we get A? So when A is equal to N1 phase divided by N2 phase, okay, and it is also the E1 phase divided by E2 phase, okay, this is equal to E1 phase divided by E2 phase. Okay, connection is given delta star. Primary windings are connected in the delta, whereas secondary windings are connected in the star. So now here primary side V1L. So this is a always, okay, here 110 kV, okay, 11 kV. Okay, it is a V1L. Always it is a V1L and the V2L. Okay, so this is connection is the delta and this connection is the star. Now substitute you will get here V1 phase is equal to V1L only, V1L because of the delta. V2 phase is equal to star connection, that's why the here V1 the V2L by root 3. So now simplify here where A is equal to, okay, 110 kilovolts divided by, okay, 11 kV by root 3. kV cancel, okay, it is equal to, okay, this value is equal to how much? Okay, A is equal to 10 root 3. Okay, this is equal to 10 the root 3 values. But we required I1 phase and I2 phase, that is a 1 by A. I1 phase in case of the delta divided by I2 phase in case of the star. So that is equal to 1 by A. What is the value of? So here A is equal to 10 root 3. So if we represent in the A ratio I1 phase is to I2 phase. Okay. So now it is connected in the star and this is the connected in the delta. So that is equal to 1 is to 10 root 3. Okay, we got it. Is that clear, everyone? So option A is a correct, right? That's correct. Option A is a correct. So next, solve this question, another one. So this was another question based on this concept. A three-phase transformer has a rating of 20 MVA, 220 kilovolts star, 33 kilovolts delta with leakage reactance of 12%. The transformer reactance in the ohms refer to each phase of the LV delta connected side. LV delta connected side. Okay. Okay. In transformer, always this is a in any transformer in the transformer. Okay. So per unit percentage impedance of the transformer refer to primary side. Percentage, okay, resistance of the transformer refer to primary side, the is equal to percentage resistance of the transformer refer to the secondary side. Okay, this. Similarly, percentage reactance of the transformer refer to primary side. Okay, so equal to percentage reactance of the transformer refer to the secondary side. Now, if we find out the percentage impedance, so this is also same percentage impedance of the transformer. So refer to the primary side. So that equal to percentage impedance refer to the secondary side. So how do we answer this question? Okay, here 20 MVA. Okay, rating is given. Okay, 220 kilovolts upon 33 kV. Okay, and so it is a star delta. Okay, star delta 1. So now what it means? Primary windings are connected in the star. Okay, primary windings are connected in the star. Similarly, secondary windings are connected in the star. So what was given in the question? Percentage reactance is given. So percentage reactance. Okay, this is equal to 12%. Now per unit reactance, what will happen? How do we get per unit reactance? So this value is equal to, okay, per unit reactance is equal to percentage reactance divided by 100. So now it is equal to percentage reactance divided by 100. So now calculate per unit reactance 0.12. Okay, 0.12, that is a per unit reactance. Got it, point? So after getting per unit reactance, so we know the formula. Okay, how do we get per unit reactance value? So per unit reactance is equal to per unit reactance. So that is equal to reactance in the ohms. Okay, reactance, actual one, reactance in ohms. Okay, so next one, the base reactance, or otherwise directly we can write in case of the impedance also. So we know that, so Z per unit is equal to, okay, Z in the ohms divided by Z base value. Okay, Z base. How do we get Z base value here? So where the Z base is equal to Z base, so that is a V base divided by I base value. Okay, V base and divided by I base. So if we know the Z base, okay, here if we know the Z base, then if we multiply by the per unit value, then we will get. So similarly, that is the per unit reactance, the refer to per unit reactance refer to x0 to the per unit value refer to the secondary side is equal to the x02 in the ohms okay, in ohms. So divided by the x2 side base value, okay, x02, that is a base value we required, okay, like this. Similarly, okay, x02a. So our x02 base is equal to x2 base value or x02 base value. So now here EB2 divided by IB2. Okay, secondary side only. That this is the VB2 divided by IB2 values. So now this one you can write. So VB2 is a, what is the base value? EB2 per base value. Okay, this is the connected in the delta side only, LV side. Okay, base values are remain same, but that is a I base is equal to, first V base is the 33 kV. Okay, V base is a 33 kV. Here this is equal to, V base is equal to 33 into 10 to the power of 3. And I base value is equal to, how do we get phase current? The root 3 times of the, okay, root 3 times of 20 MVA by, okay, here root 3 I base value, the root 3 times of this current. Okay, here 20 MVA is given, so that here root 3 times of I base 2 values. Okay, line current. Got it? This point I base 2. First find out base value. Okay, first this one is the base. X02 base value. Okay, it is equal to, so here this is a always per base manners. VB2 is a base value here. So it is equal to V base, the per base. Similarly, the why, because it is a delta connection, but here this is equal to, the first find out the line current divided by the root 3, you will get the phase current. Okay, so here delta side is a required, line current is equal to root 3 times of the phase current. Okay, here the root 3 times of 20, okay, root 3 times of 20 kV, or directly you can write, so it is the 33 kV divided by the root 3 times of, okay, 20 MVA 10 to the power of 6, okay, divided by, okay, root 3 VA line 33 kV. Okay, 30, this is the line current. Okay, now, so this is equal to, we can write VB base, or otherwise simplify here. What is the answer? Got it? Can you tell me first one, what is the Z base value? Calculate Z base or X base value. After that, find out X02 in the ohms divided by, okay, Z base, okay, multiplied by, okay, per unit value, X per unit value. I will tell you the second method also. By using this one other one, you can directly answer by this question. Now calculate this part. It is the line current. So 33 kV. So now it is equal to 33 kV square whole square divided by the root 3 times of 20 into 10 to the power of 6. Okay, it is a line current only. That's why we can take, okay, line current. So divided by the root 3. So now here root 3 will be the cancelled out. So now that is equal to 20 values. Okay, can you tell me this answer? Can you calculate? Just calculate this one. I will also check the answer once. Yes, okay, that's correct. So V base is square. This is the divided by, okay, root 3 here. So we will get the 3 times. Finally here we will get x base value. No, it is a root 3 and this is the 33 square and 33 MVA divided by root 3. So now this value is a x base 33 kV square divided by, okay, 20 MVA by 3. So now simplify x per unit value. How do you get x value here? Per 0.012. So now it is equal to 19.6. Okay, 19.6 ohms. Now have we got it? 19.6. Here no need to confuse. Okay, just take directly also. So that is the Z base is equal to, okay, here Z base means all are single phase manner. Okay, Z base is equal to VB phase per phase divided by IB phase per phase value. Okay, IB base per phase. So now VB base per phase, similar way, the X base the single phase manner in the secondary side. Okay, here in star connected side. Okay, in the star connected side. So then what will happen? So it is a XVB phase. Okay, but here this value is equal to, so here also XIB per phase value here. So now VB base value in the single phase. So now it is equal to the 33 by the 11 kV. Okay, that's correct. But IB phase, okay, in the single phase manner, it is equal to, so IL, okay, first per phase value you can write. So IL divided by root 3. So how do we get IL value? So that is a IL is equal to, we can get, that is a 33. Okay, line value is equal to, okay, it is a root 3 and line value, okay, it is a 20 MVA. Okay, root 3 times of the 20 MVA divided by, okay, this the voltage is equal to 33 kV. Okay, that's why, so you will get root 3 is a cancel, that is the 3 into the 20 MVA. Okay, here the S power is equal to the power, the root 3 times of the VL and IL. Okay, so now here VL is equal to, okay, that's the, it is not root 3. Okay, here root 3 times of this value. So now it is equal to the 20 MVA 3 by root 3 and means 3 into 33 kV. Okay, this value here IB base. So now therefore XB base is equal to in the single phase. Okay, it is a 20 year. Okay, 33 kV divided by okay 20 MVA. Okay, into MVA divided by 3 into 33 kV. So that is equal to 33 kV whole square by the 20 MVA by 3. Yes, so like this, that's why we have written here directly. Actually it is not root 3 here, so it is a 20 into root 3 times of this value. So that's why we will get 20 by root 3. Okay, all of it clear now? So now calculate one more question. This is another possibility question based on this concept. So it was GATE 2000 question. A 3-phase delta star transformer is supplied at 600 volts on the delta connected side. The terminal voltage on the secondary side when supplying full load as a 0.8 lagging power factor is a 415 volts. The equivalent resistance and reactance drops of the transformer 1% and 5% the respectively. The turns ratio of the transformer is. Turns ratio is required. How do we get turns ratio of the transformer? Okay, use the voltage regulation formula. Okay, turns ratio of the transformer. Find out by using the voltage regulation formula. It is very easy. Turns ratio means A1. Okay, let's find the answer. 22. Okay, how do we get this answer? A 3-phase delta star transformer is supplied at 6000 volts delta connected side. So what is the percentage voltage regulation? So voltage regulation of alternator, percentage voltage regulation of the transformers. So that is equal to the here percentage R cos theta 2, okay, plus or minus percentage X sin theta 2. Okay, plus is for lagging power factor, plus is for the lagging, and minus is for the leading power factors. Got it? Lagging power factor and leading power factor. So where plus sign is considered, then what will happen here? Given that 0.8 power factor lagging, so therefore percentage voltage regulation is equal to percentage R cos theta 2 the plus percentage X sin theta 2 value. How do we write percentage X value here, percentage R, percentage X here? So this equation we can write. So it is a VNL minus V full load divided by VNL the into 100 is equal to percentage R cos theta 2 the plus percentage X sin theta 2. Okay, sin theta here. So VNL in the sense the V2 minus V2 divided by the E2 the into 100 the is equal to percentage R cos theta 2 plus percentage X sin theta 2. Now simplify. Now first substitute all the values in this equation. So V2 is a given. Okay, what is the value of V2? Okay, that is equal to percentage R is a 1%. Okay, this is the 5%. Okay, now secondary terminal voltage is equal to 415 volts. Okay, calculate this part. One into 0.8 plus 5 here, 5 into 0.6, percentage X is a 5%. So now calculate this part. V is given induced EMF minus terminal voltage, so divided by the induced EMF. Okay, what is the terminal voltage? So now here V2 is a required minus terminal voltage 415 volts divided by the E2. Okay, it is equal to, calculate this one, 3 by 8 into 100. Okay, now calculate the E2 value. Induced EMF per year, induced EMF E2 per phase value is required. Okay, E2 is equal to, calculate this part, 1 minus, okay, anybody got it? What is the answer for this question? Okay, here E2 per phase value you can take. So this value also let us take V2 and here V2 here. So by using this, so we can write it is a V2 is a 415 volts. Okay, so now here this V2 is equal to, so V2 per phase value, per phase, that is the V2 is a 430.77 volts. Now let us find out V2 per phase. Okay, V2 phase value is equal to the 430 divided by the root 3. So but we required turns ratio. Okay, turns ratio is equal to the 6000 divided by V1 phase divided by V2 phase. So V1 phase the 6000, V2 phase the 430 divided by the root 3. Now simplify this, you will get nearly the 24.12. So now it is a nearly equal to 24. Like this we have to calculate. Now this is another question based on this concept. The resistance and reactance of a 10 kVA 1400 volts delta star distribution transformers. Okay, the resistance and reactance of a 10 kVA 11 kV 4000 volts delta star distribution transformers are 0.02 and 0.07 per unit respectively. The phase impedance of the transformer referred to the primary side. Okay, phase impedance of the transformer referred to the primary side. So here distribution transformer resistance and reactances are given in the per unit value. So now Z per unit is equal to, given that the Z per unit value, so it is equal to 0.02 plus J 0.07. okay, 07 per unit values. So we know that Z per unit is equal to, so what is the formula here? Z per unit is equal to, so Z in the ohms divided by, so Z in the base value, okay, Z base value. So we required Z per unit refer to which side? The refer to the primary side, that is the 11 kV side, high voltage side. So now Z per unit refer to primary side is equal to, okay, here the Z in the ohms refer to primary side. Now similar, this the Z base the refer to primary side. All our primary side is the required. So now calculate, you will get an answer here. So first find out Z base primary side. Okay, Z base refer to the primary side. How do we get Z base refer to the primary side? The VB, the single phase manner, divided by the IB, the single phase manners. Okay, so where EB is equal to the VB in the single phase manner. Okay, all our per unit value are per phase values. So that's why here VB is a single phase, it is a delta connection. So that is a VB single phase manner is equal to, okay, this is a 11,000 divided by root 3. Okay, so next one, IB in the single phase manner. So now it is a delta connection. Okay, it is a star connection, right? So it is a star connection. Okay, here given that primaries are connected in the star, secondaries are connected in the delta. Sorry, primaries are connected in the delta, secondaries are connected in the star. So that here no need to multiply with the root 3. So now this value is equal to 11,000 volts. So now IB is equal to IB in the single phase. Okay, here delta connection. So IL by root 3. So where how do we get IL value? Okay, root 3 here. So now it is a power divided by, okay, power S, okay, S in the power divided by root 3 times of the VL. So now calculate this value, you can write S is equal to power divided by root 3, so that it is a S by S by 3 into VL. Okay, now it is equal to, what is the value of S? 100 kVA. Okay, 100 kVA divided by, okay, 3 into VL. VL is equal to 11 into 10 to the power 11 in kVA. 11 kilo volts. Okay, so this is the IB base value. So now here Z base is equal to, what is the Z base? Refer to the primary side. Okay, here V base is equal to 11,000, okay, divided by, okay, it is a 100 kVA, okay, divided by 3 into 11,000, okay, 11,000. So now simplify here, 11,000 square divided by 100 kVA by, okay, kVA by 3. Okay, now Z base is equal to, now calculate first what is the value of Z base. $11,000 very important problems for gate point of view. Yes, 3630, that's correct. Okay, now find out Z base primary. Okay, after that Z in the ohms refer to the primary side. So now it is equal to, so here Z per unit value, Z per unit into Z base value refer to primary side. Now calculate this one. Z per unit is a 0.02, J 0.07, 0.02 plus J 0.07 multiplied by 3630. Now calculate this one. 360 into 0.02 into 0.02, okay, 72.6, okay, plus now 0.07 into 3630, okay, 254 J 254.1. Okay, what is the answer for this question? Yes, this is the correct. Option D is the correct. Okay, all of you got it? Okay, that's correct. Naishwar, that's correct. Okay, Z base is the correct. Then calculate Z per base impedance. Okay, so now let us solve one more question. So this is the question, another question based on this concept. A delta star transformer has a phase-to-phase voltage transformation ratio of K, where K is a delta phase voltage divided by star phase voltage. So then line to line voltage ratio of star delta transformer, star delta connection. Okay, this was IAS question. So here delta star three-phase transformer. Okay, delta star three-phase transformer. So now it is a K in the sense primary phase voltage divided by is given that. So it is a K is equal to, okay, here the K is a delta phase voltage. Delta phase voltage means V1 phase divided by, okay, star phase voltage. Okay, that is the V2 phase. So the in case of the delta star three phase transformer, and line to line voltage ratio of the star delta three phase transformer. Okay, line to line voltage ratio of the three phase transformers. So now here K is a K is a phase turns ratio only. So it is represented with a phase turns ratio. Phase turns ratio only. So then how do we get in case of the star delta three phase transformer? Okay, in case of star delta three phase transformer. So here V1 phase, okay, K in the sense the V1 phase divided by, okay, V1 phase divided by the V2 phase. Okay, V1 phase, or otherwise let us assume like this also. So let V is a V1L is equal to V, and V1 phase is equal to, okay, here V by root 3. Okay, V by root 3. So next one, the V2 phase is equal to, so what is the answer? V2 phase is equal to V2 phase, it is equal to V by, same here, V by root 3A. Now V2L is equal to, so that is also V by root 3A. So this is the formulas in case of the L. So now here K is given, where K is equal to the V1 phase divided by the V2 phase value. So now if it is connected in the star side, okay, this is connected to the delta. Okay, this is the connected in the delta and it is connected in the star. Okay, now what about the line voltage? Okay, here is a the here K, we can write this the V1L. Okay, both are the same. Okay, now V2L we can write, so that is the star connection. So V2L by, okay, root 3. Okay, V2L by root 3. So now here V1L by V2L is equal to, V1L is a delta. So now this one is a star. Okay, star value. So now it is equal to the K multiplied by the, this is a, so K by the root 3 values. So now if it is reverse, okay, root 3 by K. Okay, that is a, suppose if we take in the reverse manner, so that is a V2L. So this is a V2 in case of the star side. So that is the in star delta transformer. So star delta transformer. So V1L is equal to, okay, root 3 V1L by the V2L is equal to, so root 3 by K. So answer for this question is root 3 by K. Yes, that's correct. Like this we have to answer this question. So next one. This is also another important question based on the three-phase transformer. A figure shows delta star connected a three-phase distribution transformer used to step down the voltage from the 11 kV to 415 voltage line to line. It has a two switches as shown in the figure. It has a two switches S1 and S2. Under normal condition, S1 is a close and S2 is a open. Okay, under normal condition here S1 is a close and S2 is a open. Under certain special conditions, okay, S1 is a open and S2 is a close. Then in such cases, magnitude of the voltage across the LV terminals A and C. Okay, terminal A and C. So now these are connected in the star. Connected in the star. And this is the connected in the delta. Connected in delta here. So in star connection, we know that in the star connection, okay, star connection here. So how do we get, suppose if we write A, B, C here, so we required AC. Okay, suppose this is the, okay, VAN, okay, VAN, and it is a the VBN, and this one is the VCN. Okay, VCN. So we required line voltage between the A and C terminal. So now this is a the VA. So VAN is equal to, okay, VA VCN is a required. So now this is equal to, so VC, okay, VAC, okay, VAC here. Okay, got it point? So VAC. Therefore, we can write VAC is equal to VAN minus VAC vector, VAN minus, okay, VAC vectors. Okay, this is the we required. VAC is equal to VAN minus VAC. So now it is the VAN phase, A phase voltage, and it is the A phase and AC VAN VCN, okay, C phase voltage. Then only you will get the line voltage. So this is the formula we required to answer this question. So but here there is a conditions in the delta side. Okay, in the delta VAB VBC here, okay, line voltage, all the values are in case of the delta. When these two are connected, so let's see. So in delta connected side, okay, in the delta, side, okay, so here all are like this we have taken. Okay, suppose it is the A and this one is the B. Okay, now this is a C terminals. Okay, A, B and the C. So now what will happen in the delta? Phase voltage, line voltage, both are same. So in the delta connection, phase voltage the equal to line voltage. Okay, line voltage is here. So therefore here, so this you can write VAB plus VBC plus VAC. VAC is equal to 0. Okay, here by KVL equation here. By KVL equation. Now what about the VBC value here? VBC. So VBC, where VBC is equal to the VBC, so that is the VB. VB1 B2 is equal to the VC1 and C2. So but when switch is closed, okay, now this is equal to, so same potential, so 0, VBC is equal to 0 because when the S2 is a close, okay, S2 is a closed here. So what is the reason? When S2 is a close, so this is the same potential here. Okay, when S2 is a close, B and C is the same potential. So that's the voltage across these two terminals is equal to 0. VBC is equal to 0. When VBC is equal to 0, then what will happen? When VBC is equal to 0, so VAC is equal to, okay, here minus the VAB values. Okay, so this is the formula is required to answer this question. So VAC is equal to minus VAB. Okay, minus VAB1. So therefore we can write, so in secondary side, so what is the formula here in the secondary side? So VAC is equal to, so now it is the VAN minus the VCN. So now it is equal to the VAC. Okay, this value is equal to, okay, here we will get VAC vector. Suppose VAC is a, that is a VAC and VBC is equal to 11,000 divided by A. Okay, at an angle of the 0. Okay, minus of, okay, this is the 11,000 and at an angle of, okay, minus VAB in the sense 180-degree phase displacement. So now at an angle of, okay, this is the by A values here. Now where A is equal to 1 by A, so now this value is equal to the 11,000 at an angle of the 0 degrees minus 11,000 at an angle of the 180 degrees. Okay, now simplify, you will get an answer. Where A is called phase turns ratio, calculate phase turns ratio, you will get an answer. Okay, so now here this value is a phase turns ratio. Simplify, you will get, so nearly 480 volts. When the switches are closed here, this will, the potential of this one is the remain same. Potential of the this space and potential of the this space the same. So that's why VBC is equal to 0. When VBC is equal to 0, so now when A is equal to, find out A, the A is the V1 phase divided by, okay, V2 phase. The what is the value of V1 phase? Okay, here the 11,000 divided by 400 by root 3. 415 by root 3. So now substitute here, you will get a answer nearly equal to 480 volts. Okay, got it all of you? Is that clear everyone? So now solve this question. Another one. A delta connected transformer is connected to the open delta connected transformer. The ratio of VA rating of open delta connected transformer. Delta connected transformer is connected to the open delta connected transformer. The ratio of the VA rating of transformer, delta connected transformers. So what is the answer? The capacity of the open delta connection. Capacity of open delta connection divided by capacity of closed delta connection. Closed delta connection. So open delta connection is equal to 3 times of the V pace and I pace. Okay, V pace and I pace value. Okay. Sorry, root 3 times of V pace and I pace. Now capacity of the closed delta here 3 times of the V pace and I pace value. Okay, these two will be the cancelled out. The V pace and I pace is the cancelled out. So now here therefore you can write capacity of open delta connection. Open delta connection is equal to 1 by root 3 times of the capacity of the closed delta connection. Okay, now it is equal to 1 by root 3 means 57.7%. Okay, capacity of open delta connection. So that answer here into capacity of closed delta connection. Okay, answer, this A answer is a correct. Very good. Now let us solve one more question. This was GATE 2008 question. It is a very important model in case of the three-phase transformers. How do we answer this question? Primary side are connected in the star, whereas secondary side are connected in the star. So it is the outgoing terminal is a A2, B2, C2. Here is outgoing terminal is a A2, B2, C2. Okay, here. So these are connected to the neutral point. Okay, here is a connected to neutral point. So now here A phase winding, B phase winding and C phase winding. Similarly here also A phase winding, B phase winding, okay, C phase winding. Okay, primary winding terminals are represented with the capital letters, whereas secondary winding terminals are represented with the small letters. Okay, this is a very important formula. So now how do we answer this question? So here A phase winding, okay, primary A phase winding, primary A phase winding, connected between A2, okay, A2 and neutral point. Okay, like similarly primary B phase winding connected between B2 and the neutral point. Like the primary C phase winding connected between the C2 and the neutral point. So here outgoing terminal is this A2, B2, C2 are the outgoing terminal. Now similar way, what about the secondary windings here? So A phase winding connected between A2 and A1, but A1 is connected to B2 terminal. So that here secondary A phase winding secondary side. So A winding or A phase winding, the connected between the A2 and the B2 terminals. Okay, A2 and the B2 terminal. So now here B phase winding connected between, so that is a B2 and B1. Again B1 is connected to the C2 outgoing terminal. So that it is a B2 and the C2 here. Next one, C phase winding connected between the C2 and A2 terminals. Okay, got it, pen? The A phase winding connected between A2, B2, B phase winding connected between B2 and C2, whereas C phase winding connected between the C2 and, okay, ఈ టెర్మినల్ చూసుకోవాలి, అవుట్ గోయింగ్ టెర్మినల్. ఇయర్ యాక్చువల్లీ ఏ ఫేస్ వైండింగ్ అనేది A2 కు A1 మధ్యలో కనెక్ట్ అయింది, కానీ A1 connected to the B2 terminal. That's why A phase winding connected between the A2 and B2, B phase winding connected between the B2 and C2, whereas C phase winding connected between the C2 and A2 terminals. Okay. Now let us draw the vector diagram. So voltage vector diagram. How do we draw this vector diagram? See, first one, the while drawing the primary A phase vector. So that is a primary A phase vector must be coincide with the 12 o'clock position. Okay, it is a A2 terminal. Okay, outgoing is a A2. This is the A phase vector. So next one, after this, the B phase winding. Okay, outgoing terminal is the B2. So it is a B phase winding. And after that, okay, C phase winding. Okay, it is a, so C phase winding, outgoing terminal is C. So now verify the phase sequence here. Phase sequence, so that is equal to ABC phase sequence. Okay. So now similar manner we have to draw the secondary delta connection. Okay, secondary delta connection. So now A phase winding connected in phase with the here outgoing terminals are the same. This is the A2, A2, A2 and E. If outgoing terminals are same, draw the secondary A phase winding in phase with the primary A phase winding. Okay, in phase with the primary. So that's why we can draw here secondary A phase winding in phase with the primary A phase winding. So this is the A phase out, that is a this is upward direction. So that's why it is a secondary A phase winding. Okay, here I am writing the secondary A phase winding. Outgoing terminal is a, okay, here A2. If it is a A2, so definitely this point here B2 terminals. Got it? So A2 and B2, this vector is a, so here A vector. Okay, here is a vector here. So next one, outgoing terminal. Okay, is a B2 is a outgoing terminal. A vector line. Suppose if it is, if I take the C here, into the A2, B2 to get the delta, C is either here or this position. Okay, otherwise I will take, so another diagram. Suppose it is a, the B2, okay, it is a A2 terminal and this one is a B2 terminal. Either C2 comes here, okay, at this position here C2, or otherwise here is a C2. There is a two possibilities. Either C2 comes left hand side of this the line or right hand side of the this line. I have taken two possibilities. So let's verify. Okay, next one. So B phase winding. Okay, here is a, this is a phase. Now B phase winding, the in phase with the secondary B phase vector, in phase with the primary B phase vector. So secondary B phase vector is this direction. So that I am writing secondary B phase vector, okay, in phase with the primary B phase vector. Okay, it is the B. Next one, secondary C phase vector in phase with the primary C phase vector. So now it is the C phase. So now let us verify the phase sequence. The phase sequence. Okay, phase sequence. Suppose it is a secondary A phase vector in phase with the primary A phase vector. Or the next one, secondary B phase vector in phase with the primary. If it is a C here, so this is the direction here. This is the B. Okay, now this one is a secondary C phase vector. Here is a the C phase vector. So but what is the, what will happen? Which one is the correct? Here also phase sequence is same. The phase sequence. So it is a ABC phase sequence. Now this is also the ABC phase sequence. But here A phase connected between the A2 and B2 terminal. B phase connected between B2 and C2 terminal. Okay, C phase connected between the C2 and. But here see, A phase winding connected between A2 and B2. B phase winding connected between A2 and C2. So that's why it is a wrong. Okay, it is a wrong. So now which one is a correct? This diagram is a correct. Okay, so like this we have to take. Suppose here actually A phase winding connected between, okay, A phase winding connected between A2 and B2, B phase winding connected between B2 and C2, C phase winding connected between C2 and A2. But in this diagram, A phase winding connected between A2 and C2. Okay, but actually it is a A2 and the B phase winding connected between B2 and C2 terminal. So that's why this vector diagram is correct. So after getting this, so convert into equivalent, okay, equivalent, the star, okay, equivalent star. So now this is the equivalent star connection. Okay, still, okay. After convert చేసిన తర్వాత, so this the intersecting the line represent the A phase, okay, A vector, okay, A, and this the small a, right, okay, A, and this the outgoing terminal is a here B2. So now here is a A2 and here is a C2. So that's why this is the C and this is the A and this is the B. Okay, like so now compare with the clock notations. How do we get? So now here this is the A point, A vector, okay, A vector here. So next one, so this is a the A vector, the it represents the minute hand, already mentioned here, the minute hand here. So now this is the B here is a small a vector, so it is a small a, it represents the hour hand. So now it is a dy1, dy1. Answer for this question is dy1, sorry, not dy1, yd1. So primaries are connected in the star, right? Secondaries are connected in the delta. So that answer is a yd1. Okay, got it my point? How do we get this answer? Very, very important question. Like this we have to answer this question. Okay, so now solve one more question. So this is another question based on the three-phase transformer. The star side of the star delta transformer shown in the figure is excited by the negative sequence voltage. Then, so what is the phase difference between? Okay, this is the negative sequence voltage. So what will happen in case of the star connection? So let assume that let V1 is a V1 is sorry V is a supply voltage. Okay, supply voltage, got it? So now the V1L is equal to, okay, V1L is equal to V at an angle of the 0. Okay, V at an angle of 0. So next one, the V2L is equal to V2L, or otherwise we can take V1 at an angle of the 0 values here. So this is the we have taken V1L is equal to line. So in the negative sequence star connection, so what will happen in the negative sequence star connection? Line voltage leads the phase voltage by 30 degrees. Okay, the leading or lagging position. Suppose this is a VA and after that VC per negative sequence. Okay, VC, and this one is the VB, right? So now we require line voltage, that is a VB here. So vector sum of these two, okay, it is a VAB, So now it is a per negative sequence. Okay, negative sequence here, so that you can write in star connection. In star connection, okay, line voltage leads, so line voltage lags the phase voltage by 30 degrees for negative sequence here. For positive sequence it is a leading position, for negative sequence it is a lagging position. So that we can write VL is equal to, okay, VL is equal to the root 3 times of the, okay, root 3 times of V phase at an angle of the minus 30 degrees. Okay, this is the formula is required. So to answer this question, okay, to answer this question here. So now we required, here is a capital AB is given. So therefore you can write capital AB is equal to the root 3 times of the some phase V1 phase. Okay, so then minus 30 degrees here. Okay. Now calculate. So here VAB is equal to V1L. So that is equal to root 3 times of the V1 phase. V1 phase at an angle of minus 30 degrees. Okay, minus 30 degrees. Okay, VAB is equal to minus 30 degrees. So from here we can write V1 phase is equal to, what is the answer? V1 phase. V1 phase is equal to V1 phase is equal to V1 L by root 3 at an angle of plus 30 degrees. Okay, and V2 phase is equal to, so now it is a star connection delta, this is a V2 phase. So now it is a V1 phase divided by A. So now it is equal to plus 30 degrees, right? Plus that. So next one V2L is equal to delta connection. So now it is equal to V2L. So that is the V by, okay, V by L. This is the V2 phase is equal to. So now suppose if it is a V1L is equal to 0, the here. So now what will happen? V1 phase is equal to V1L is equal to V at an angle of the 0. So now this is the V by root 3 plus 30 degrees, right? So now it is equal to VAB. Okay. So now this is equal to V by root 3 A plus 30 degrees. Now this one is a V2L is also equal to write same, the root 3 V by L plus 30 degrees here. So plus degrees means V2L is a small AB. So now we can write, if it is a reference, suppose if we take I have reference, so then what will happen? VAB here, VAB, the lag leads the, okay, leads the VAB by 30 degrees. Okay, 30. Suppose if it is a reference, if I take this the reference, so then what will happen? So now it is a VAB, okay, lagging. Suppose here is a VAB, I have taken the reference. So now this is a, okay, it is a reference. So then it is a VAB values, okay, leading by 30 degrees. Suppose if I take this value as a reference, so VAB lags, okay, VAB by 30 degrees, okay, 30 degrees here. So now what will happen? This one, suppose if I take VAB, So reference, then the capital AB here lagging position. Okay. So now answer for this question. Anyone can answer this? Okay, VAB lags VAB by 30 degrees. VAB lags VAB by 30 degrees. Okay, so VAB lags VAB by 30 degrees. So any other given? VAB leads VAB. Okay, this is a reference is the VAB. So now it is equal to, so that option B is the correct. Okay, so now solve one more question. Okay, this is also another possibility question based on this concept. Two three-phase transformers are realized using single-phase transformer as shown in the figure. So first one, this is the all are connected to the same supply. So this is the delta connection and this is the delta connection. So now here is a, so delta star the three-phase transformer. Another one is also the delta star three-phase transformer. No, it is a delta three-phase transformer and delta star three-phase transformer here. So phase displacement between these two here 0. But we required phase displacement between these two here. So this is a delta secondary side that here one transformer is connected in the delta, one transformer is connected in delta, and other transformer is connected in star. Okay, so what is the phase difference in the degrees is required? Phase difference between the between the delta and star connection. So that is the here 30 degree, either 30 degree lagging or 30 degree. So V1 and V2 is a 30 degree phase difference. So it is the same question. So now here in the two-limb three-phase delta star connected transformer supplied from the same source, one of the transformer is a DY1. Okay, first transformer 1. Okay, and transformer 2 is a DY11. Then the phase difference between the DY1 is nothing but here DY1 is a minus 30 degrees. Okay, 30 degree lagging. Okay, now DY11 in the sense it is a plus 30 degrees. Now what about the phase difference between these two transformers? The phase difference between these two transformer. So now it is equal to plus 30 degrees minus of minus 30 degrees. So now it is equal to 60 degrees. Okay, got it? Now let us solve one more question based on this concept. Which of the three-phase connection can be used in a transformer to introduce phase difference of 30 degrees between its output corresponding to the input voltage? Star delta, star star, delta delta. This is the delta zigzag star. So these are all are, this is the 0 degree connection. 0 degree connection only. Okay, and this is also 0 degree connection, and this is also 0 degree connection. So introduce the plus or minus 30 degree connection. It is a plus or minus 30 degree connection. So to introduce the phase difference of plus or minus 30 degree connection, so this is a star delta transformer is a suitable. Okay, got it? Yes, star delta, that's correct. So next one, solve this question. This question based on the parallel operation of the transformers. So two single phase transformers are connected in parallel to share a load of the 1000 kVA. To load of 1000 kVA. Okay, rating of the transformer and their impedances are given. So transformer A is a 800 kVA. Transformer the 800 kVA XA is equal to 2 ohms. Transformer B is a 400 kVA XB is equal to 2 ohms. kVA shared by the transformer A. Okay, transformer A. If XA XB are given in the ohmic values, you can substitute directly. Okay. Therefore, the here kVA shared by kVA shared by transformer A is equal to, so what is the answer here? Load kVA divided by the impedance of the transformer. Just apply the parallel connection principle. Okay, this is a ZB by ZA plus ZB values. So now I'll substitute this value. Okay, ZA by ZB values. What is the answer? Load kVA multiplied by ZB into ZA by ZA plus ZB values here. Load kVA is 1000. The ZB is equal to, okay, here resistance is neglected, so that here directly you can take 2. So now this is the ZB, or otherwise we can take, resistance is neglected, then what is the answer here? So this is equal to the load kVA the into the XB divided by the XA plus the XB values here. So therefore we can write load kVA is a load kVA is 1000 into XB is equal to 4 divided by 2 plus 4. So now simplify, you will get this. Similarly, the kVA shared by the transformer B. kVA shared by transformer B. So that is equal to the load kVA the into XA divided by XA plus XB value. So what is the answer? Okay, that is equal to, so here 1000 kVA into here 2 divided by 2 plus 4. So now calculate, you will get an answer. Okay, that is a 4 divided by 6 into 1000. So that is this value is equal to, this value is a 66.66 kVA. Okay, and calculate this one, 2 divided by 6. Okay, it is a 33.33 kVA. Okay, like this we have to answer this question. Now let us solve one more question based on this concept. Okay, two single phase transformers are connected in parallel to share a load of 1000 kVA. Rating of the transformers. Okay, rating of transformers. Two single phase transformers are connected in parallel to share a load of 1000 kVA. Rating of the transformers and their impedances are given as follows. So per transformer A 800 kVA XA is equal to 2%. Per transformer B 400 kVA XB is equal to 2%. Find kVA shared by the each transformer. If in the previous question XA XB are given in the ohmic values, but in this question XA XB are in the given in the per unit values. So that's why we have to find out the new per unit values. How do we find out new per unit value? So XA new is equal to XA new. So that is the assume as a initially. So XA new and XB new value we have to find out. So how do we find out this XA and XB value? Okay, to get this XA and XB value we have to take one common base value. So now let us assume here the let common common base kVA of the two transformer. So that's I have taken 800 kVA. Okay, that is the kVA rating of, okay, that is nothing but you can take kVA rating of transformer B also, there is no problem. So that's why XA new is equal to, so that is the here the XA old, okay, that multiplied by kVA new divided by kVA old. Okay, this is the formula. So now how do we get this XA old? So it is the 2% means 0.02, okay, multiplied by per unit values. So here the this is the XA per unit value, XA per unit 0.02 and XB per unit value is a 0.04. So now it is equal to 800 kVA divided by 800 kVA. So now it is equal to 0.02 per unit. Okay. So now next one XB, the new per unit value is equal to, so XA volt per unit value, XA volt per unit, sorry, XB volt into kVA new divided by kVA volt. So what about this XB volt here? So it is a 0.04 into the kVA new is a 800, okay, divided by 400 kVA. So now it is equal to 0.08, 0.08 per unit value. So now this is a X by new and XA new value, XB new value. So now substitute to find the load shared by the each transformers. So find out here load shared by the transformer A. So that equal to, how do we get the load kVA the into the XA by XA plus XB value. Okay, XA plus XB. So now this value is equal to, so now what is the load kVA? 1000. Okay, 1000 only. 1000 multiplied by XA is a 0.02. So now this is the 0.02 plus 0.08. Okay. So now calculate, you will get answer. Load shared by transformer B. Okay. So what is the formula here? The load kVA into XB divided by XA plus XB value. So load kVA is 1000. The into XB is equal to how much? XB value. Okay, 0.08. So divided by 0.02 plus 0.08. So now simplify, you will get a answers. Okay, this is a 1000, 0.02, 0.02, 0.02 plus 0.08. Okay, 0.02 divided by 0.2 into 100, so 1000. So it is equal to, now it is a XB values, not XA. Okay, transformer A and it is a XA. Okay, load kVA shared by the transformer A, XB divided by XA plus XB. So now it is equal to 800 kVA and this is a we will get 0.08 XCA it is a 0.08 0.02 0.02 divided by 0.1 okay into 1000 okay now it is equal to 200 kV okay like this we have to answer this question okay load shared by the transformer A is equal to okay load kVA into XB okay divided by XA load shared by the transformer B is equal to load kVA into XA where XA is equal to 0.02 XB is equal to 0.08 so now calculate 800 kVA and 200 kVA one transformer is operated in the rated condition another one is under rated condition. All of you clear now? So these are the questions based on the three-phase transformer. So we have some other questions we'll discuss in the next the question series. Okay, there are the two question series in the three-phase transformer. One is the question series 1 and question series 2. Okay, in the question series 2, we'll discuss remaining part. Okay. Yeah, that's correct, Nageshwar. So I have written directly XB XC air. Okay, 800 kVA and 600 kVA. Okay, these are some questions. We have many more questions are there based on the three-phase transformer. We will discuss that part in the next series. Okay, so we have some other questions are there that we will discuss in the next series. Thank you all. So this is a official Creatrix channel which has 150k plus members. Please join in this channel. Okay, it is Unacademy GATE Telugu channel. Okay, it is different type of channels under the Unacademy. So the one is a Creatrix GATE Electrical, okay, Unacademy GATE Mechanical, Unacademy GATE Civil, Unacademy GATE Telugu. So this is our channel. Please like and share, subscribe this channel. Unacademy GATE SSCJE, Unacademy Computer Science, Unacademy GATE Questions, Electrical Junction, Engineering Foundation and Engineering Pathshala. Okay. So thank you all. Thank you very much.